Thanks everybody for showing up. This is a much different talk than the ones you've been used to hearing. So this is a hardware talk. So my name is Tom Palkert. I am the chair of the SFF, the SNIA SFF Transceivers Group. Anthony is in the back, and he's the co-chair of the SFF group. And I'm also chair of the fiber channel physical layer. So I'm very much a physical layer guy, connectors, transceivers, SerDes, high-speed interconnect, things like that. So I'm here to talk about is we are trying to decide as Jay and the group talk about what we're going to do for AI. We've said, okay, what can SFF do? And one of the things we're looking at now is how do we play in this a newer high-speed area for AI. So we are working together with a bunch of other standards groups you'll see in a little bit here to try and accelerate the adoption of 400 gig or higher speed AI interconnects. So I thought I'd start with the usual slide about AI stuff. And so what we're talking about, a lot of work here, so you got the NVLink and UA link go from GPU to GPU, and these also go across these GPUs on a single card, or whether that definition has been used today. We've got PCIe going this way, and then we've got Ethernet and UEC going out in the front end, and these NIC interfaces here. So what we're doing at SFF is we are primarily focusing on these copper interconnects here. So we are going to avoid the optical ones and leave that to IEEE or OIF or some other standards group. And we're going to focus on these connectors, channels, and interconnects here. And you'll see, if you maybe think about a high-speed interconnect, you think, okay, it's a chip going into a printed circuit board, going over to some other chip, and they run really fast. Well, you're going to see now that is going to change pretty quickly as we get into these higher speeds. It's now going to be a lot of different options you can do there. So first thing we looked at is what's needed for AI copper, right? And so the things that we got from people here is, number one is maximum reach. So they want to go as far as possible. So we've defined basically down here, this is a DAC, stands for direct attached copper. So that's your copper wires. ACC is an analog amplifier inside a copper cable, and it goes, you can see here, this is like 1 meter. That's getting up to like 3 meters. And AEC is a retimer. It's like a DSP inside a copper cable. That goes up to about 5 meters. And then if you go optical, and this LPO, this is a linear optical, active optical cable, so it has no optical connector exposed. It looks just like a copper cable, but it has optics inside. And that can run up to 30 meters, which is the specs we're being given by the AI guys. I think those numbers were mentioned in some earlier presentations. So, and then also we have the usual stuff, which is make it a super high density, make the connectors very high bandwidth. We're going to need to improve the host DSP capabilities. They want low bit error rate and low latency. Those are kind of the usual things we always hear every generation. So now, as I mentioned, I'm going to get into some of these channels. So if you're going to run 400 gig, the premise we're starting off with is that you probably are going to have a tough time going into the printed circuit board. So what's been demonstrated now is what we call CPC, which is co-packaged copper. And that means there's a IC, a silicon die, that's going to drive through the package, not into the printed circuit board, just through the package substrate. And on top of that package, you're going to have some kind of a soldered on or potentially pressure fitted socket on top of the package. And it's then going to have these twin-ax cables. They're going to run over to another package over here. And these are two GPUs talking to each other at very high speed. And what happens here is the signal integrity of this interface is very good, right? We can get very good SI because we don't have vias and stubs and escape things on the printed circuit board. And so we're able to achieve very high performance using this. If any of you went to OFC, I know it's a storage group, but OFC, there's a lot of demonstrations of this kind of interface. And if you've heard of co-packaged optics, this is very similar to that. This could be an optical device here also. In the same footprint. So what do you do if you want to go between two boards? So you have the same thing here. You have your co-packaged copper connector, and then you have this same twin-X cable, but now it's going into a pluggable backplane I/O connector. And again, no printed circuit board. There's power and ground coming through this connector, but there's no high-speed connections. That goes through a backplane. Cabled backplane, which again could be passive copper, active electrical, different options here depending on the distance. And then you see the same thing on the other side. And then down here, I'm showing the same thing, except here's an active element inside the cable. So inside this connector, you're going to put a chip. You're going to put an analog amplifier or a DSP amplifier in there, and that's going to allow you to achieve more distance here. Because as I mentioned, our marching orders are maximize the copper cable distance between two GPUs. So we're doing everything we can here in these slides, right? We're doing this co-packaged copper, we're doing these flyovers, we're doing amplifiers inside the cable. And this is all to increase the distance of a copper wire, okay? So in this case here, the channel that we have to define, which we're going to simulate, and I don't want to get too much detail. We have a simulating tool called COM, Channel Operating Margin. It takes into account all these signal integrity parameters and amplitudes and everything like that, puts them all together into one tool, and we simulate that from this silicon die ball right there, or bump, to that bump right there. So this is the next step also, is to take into account these package parameters, because in the past it used to be no big deal, you could ignore them. Now they're a big part of the budget. So for this one here, we have the same thing, except now we've got all these backplane connectors and cables, which adds another level of signal integrity problems. And then the last one here, you just have, again, you're going to try to simulate this straight through this active element. And if it's an analog amplifier, we can probably do that. If this is a DSP, you're going to typically have to break that into two segments to get that to simulate correctly. So, as I mentioned, there's lots more. So we've got, this is a optical module. So here you'll see this could be a co-packaged optics device. So this is actually could be an optical device here with a fiber optic cable coming off, and that runs to an optical connector on the front panel. So this is nothing but a feed-through optical connector. This is capable of achieving very high densities. Obviously, you can run thousands of these fiber optic cables. So this achieves the density that you want. And if you've been following NVIDIA's announcement, they announced that for their next generation, they're going to go 100% co-packaged optics. So that was a big deal. A lot of talk about that. And by the way, personally, I'm not a fan of that. I do not think this is going to succeed, which is why we're spending a lot of time on this co-packaged copper, because I think that's a much more viable solution. So here's the option here of going into a printed circuit board. I mentioned we have yet to see a working simulation or tool that shows that this actually will achieve 448 gigabit per second interconnect through this printed circuit board. But I just saw something this morning that shows some potential for that. So there's a possibility that we might see something there. And here, the co-packaged copper to a pluggable transceiver. This is similar to what we showed before, except this this connector here is a pluggable connector, so it's much different than the backplane connector I showed you before. And it has its own signal integrity challenges because that module has to plug in, unplug and plug in a number of times, and the pads have to line themselves up. And that has been very challenging because if you're familiar, the fiber channel guys are here in the second row. SFP modules have been very popular with fiber channel and storage, and they've been used since, what was the slowest speed we ever did in SFP? 1 gig? Yeah, at 1 gig, that same pad and socket design is still being used today at 200 gigabits per second. So the pads are getting smaller, tolerances are getting tighter, but it's still fundamentally designed used. And the industry kind of agreed that was never going to work at 448. This morning, I saw an OSFP simulation channel that showed that it could possibly work. So we may see that exist for one more generation for a pluggable module. So down here, similar thing, except this printed circuit board trace is very short, and that may allow some of this channel to work at 448. And the same thing here, you can run, this is a flyover cable, this is a twin X cable, and you can do the same thing here with a near package optical module where the copper trace is very short and then it runs optics across here. So there's a number of these things, again, that have been demonstrated in the industry, and there were a lot of them at OFC last month. So in this case here, what are we going to simulate at SFF? We're going to try and simulate that little tiny channel right there. And here we're going to go all the way to the pluggable transceiver. We get beyond the pluggable end of it. We actually take half that pluggable module and we put it in the model just to make sure we've taken everything into account. For this one here, the channel is from the die out to the transceiver, similar to the copper, this one over here, except it's all this co-packaged copper and flyover. Similar thing here, except in this case here, we've got this added connector thing down there that we've got to take into account. And then the last one here, you can see it's just a short printed circuit board to the near package optics. So these are similar, but as I mentioned, these connectors are different. So that's all we're all gonna have different modeling for each one of these different channels. Oh, can we ask questions till, no, just kidding.
First option, you said you didn't think that would be viable. What's the reason?
So this is co-packaged optics. You can see this fiber is coming off of here. And I don't want to say the worst case, but putting a laser down inside that package, as you can imagine, the thermals for this GPU are just astronomically difficult.
What was the question?
Oh, thank you, John. I was asked to repeat all questions. He was asking for my personal, I mentioned that I do not believe that CPO, co-packaged optics, was going to be successful in the market, even though NVIDIA has made a huge announcement saying they're investing everything into this for their next generation. They're going 100% co-packaged optics. So my opinion was it's not going to succeed. I spent a lot of time at OFC on panels explaining why that was the case. And so the question was, why do I not think that's going to happen? And a couple reasons. Again, I've got entire papers on this, but if you look at this, in one case you have a laser sitting there, and it's sitting on top of this just megawatt. I'm not sure, what does a GPU dissipate in terms of power? It's hundreds of watts, right? And very difficult to cool. So you're going to put this laser, which hates being hot, on top of something that is by definition the hottest thing in the thing there.
Their proposal is to have a laser pump.
Exactly. So the second one is you take that. You actually plug in one of these pluggable transceivers over here. This is defined by the OIF, actually has a huge laser in it, and it powers a lot of stuff. So you plug one of those in, and then you have that's probably more like this. And it has a fiber that comes out of it, okay? And that fiber connects to that CPO device. So the laser is now outside. It's pluggable, so it can be removed, right? And that solves some of that problem, right? So that's not a bad way to go. It has its own issues, and now you're running fiber across there and things like that. It's another single point failure. If that one pluggable laser goes down, you take down lots and lots of channels. The other issue, a big issue I have with this is actually Andy Bechtolsheim from Arista is always kind of a bellwether in the industry, and he shares the same, he had a presentation similar to mine, and he's like, okay, what if this fails? What if that device there, which is a modulator, has fiber coming in, fiber coming out, a lot of very critical things in there, what if it fails? And the answer is you're just screwed, right? Pardon me?
It's more like what happens when.
Exactly. So reliability, as NVIDIA has made many presentations, right? They've even stated their entire GPU structure from the one they did last year was all copper. And the reason it was all copper is because optics couldn't even come close to their reliability requirements. So they said everything is copper, and now they've said they're going to go all optics with the most unreliable optical thing you can think of. So it's just, I don't see it. So again, I can have a long discussion on that one with people. Okay, so what are we going to do at SFF? So as I mentioned, we're working with these other groups, and we're trying to kind of feel out where everybody's going to go. And when SFF, as Jay Metz mentioned this morning, SFF is joining the mighty SNIA organization. We're kind of all coming together. It's like, how can we work together as this transceiver connector group with the rest of SNIA? And we're trying to figure this out. And here's the thing that we're looking at right now is we're going to introduce all these channels I just showed you. So we have different customers, connector people that are going to introduce these channels. And we're going to then run this software on them. And these COM parameters here are like DSP parameters. We're going to assign what the DSP is capable of doing, run all sorts of options for that, and see if we can come up with a one that everybody will agree to. We're going to then define the package, as I mentioned. This is ERL is like think of it as a return loss parameter. We're going to look at the different PAM modulation. The world is all PAM4 right now at 448. Looks like it might be PAM6. So that's going to be a big difference there. And then we're going to look at this link training, how we're going to tie these two ends together and have them talk to each other and make that work. So the other thing that came up, and this was actually mentioned by Microsoft, by a couple people from Microsoft who have talked about this now, is they've come out and they've said that 448 may not be the best solution for the next generation of AI. He actually believed this was Pradeep, he was the founder of Juniper Networks, who's now at Microsoft. And his premise is that 200 gig is actually a better sweet spot for AI than 448. So he wants to see better, faster, more reliable, better bit error rate, better performance at 200 gig. So we're going to take all this stuff I just showed you, all this co-packaged copper, all these high bandwidth channels, and we're going to apply them to 224 gig. And we're going to say, hey, what can we do better at that speed? Because at least a couple of guys have said they'd rather go slower and better than the higher speed. And then one key thing here is our group at SFF, we do mechanicals. We are the guys that define the mechanicals around all these connectors and cages and transceivers that are used in the industry. And everybody's assuming that this is what we're going to do. And for this first project, we will not define a mechanical connector. So hopefully that's the next stage, but for this stage, we will not be defining that connector yet. And then you can look for details, go on the SNIA website. It's got a project start, SFFTA 1043. So one of the things I mentioned is that this whole thing started when we had Ethernet Alliance sponsored a 400 gig, what they call technology forum. It would have been October of 2023, I believe. No, 2024, just last year. And the hyperscalers stood up, at least 3 of them stood up and said, you know what, for instance, I'll use an example. IEEE, if you follow that work, they are currently defining a 200 gig interface. 200 gig optics, 200 gig copper, 200 gig everything, right? That project is not done, and it probably won't be done for at least another 8 to 12 months. So the hyperscalers said, we are done with 200 gig. We're deploying 200 gig. We don't care what you're doing because we have decided and we're moving on. So they told the group that if you want to be relevant at 400, you better start now. So we all got together and took that and said, okay, what can we do? So in theory, we're going to divide and conquer this problem. Not exactly sure if that's going to happen, right? Because we're going to step on each other's toes because, as I mentioned, the world thinks that we're just a bunch of connector guys, and now all of a sudden we're doing some channels. That may be, other people may think that's their side of it. But right now, we're going to stay, my proposal is that we're going to stay with a storage compute backplane focus. We are not going to talk about networking kind of things. Now, UEC is obviously talking about some networking stuff. And we may want to work with them, and we have had discussions with them. But anyways, IEEE, as I mentioned, still has to finish up their project. So we're going to start this copper work ahead of them and probably liaison or send over the results of that to them. And we already have this liaison relationship between the NEA is their sort of precursor to a project. So they've started an NEA project or NEA activity, and we're currently talking to that group. OIF has started a project to define the requirements for a connector. So for instance, they are looking at doing a 32-lane connector. As I mentioned, everyone wants more density. Currently in the industry, there's a single-lane SFP, a 4-lane QSFP, 8-lane OSFP, and a 16-lane OSFP. There's no 32-lane device in the industry. And again, the end users have said, we want a 32-lane device to achieve more density. So they're looking at whether that can be done. And they're going to give us some requirements for that connector, and we're going to give them feedback based on their connector requirements to say, you know, it just can't be done at 448, or here's a change you need to make this thing work. OCP, if you're familiar with them, is Open Compute Project. They're sort of an overriding system level group, and I know a lot of guys have liaisons with them, so we talk to them all the time. And then the last one, UEC and UA-Link, we are asking them for channel requirements, and we're going to give them feedback on their what the copper interconnect can be. So we've started this, and I mean, for instance, UEC right now, if you look at I'll take a shot at them. I don't know if anybody's here from UEC, but at what Jay showed this morning, at the bottom he said they referenced all the 100 gig Ethernet specs. Well, I can tell you right now that they do not use all the only Ethernet specs. The industry for AI has gone beyond the 100 gig Ethernet specs. They use whatever it's sometimes called LR+, sometimes called extended reach. But in my opinion, nobody in the industry is using IEEE copper spec. That's old and gone. So we're going to maybe help them out doing some of those channel requirements. So I think I might be done. Oh, I've got a couple slides just to promote, because we'd love to have you guys join us, anybody interested, or other members of your company. So right now we are SFF, and we have 72 companies. We publish 150 specs. These are where our specifications are used. A lot of, everybody references our connectors, our modules, and things like that. We do PCIe kind of stuff. We do networking kind of stuff. So we kind of cross both ends of it, and Anthony is more the expert on the other side than I am. So in the last 12 months, we've done 4 new specs, and we have some specs we update every 6 months to a year. So we're keeping moving on that. So what do we do that's network focused? This, again, is most of the stuff that I do in my group. So transceivers, we do SFP, QSFP, and those. And we do module cages, connectors, and transceivers. We define the whole pluggable thing on the I/O. And believe it or not, we spend an awful lot of time on management of those interfaces. We spend hours we spend a lot of time just defining what those codes are and how to manage these modules. And Anthony's in the back, and he's going to answer any of your questions you have on copper link and PCIe stuff. And here's other form factors that John is laughing because he's going to answer these questions. And I mentioned management stuff. I do a lot of the work in a lot of the management interfaces for transceivers. These guys work on the management for. Mike, are you answering those questions? So 224. So we have 2 families that we're working on now, SFP and QSFP. So just to let you guys know, QSFP, all our updates are in progress. I'm editing this document, and we're hoping to release it pretty quick. 1027 is this pluggable module. I mentioned it's got the connector cage and module in it. And this is the QSFP one. And then down here, we do something that's a little unique in the industry. For instance, we started doing this general electrical spec for a CDFP module. And if you're familiar with that, it's actually used for PCIe. We went to PCIe and said, hey, we're kind of working on this. And they're like, what are you doing that for? We have all this covered. And we explained what we do for General Electrical, and he's like, oh my God, this is the greatest project in the world. So now PCIe likes what we're doing. So we do things like inrush current and current carrying capabilities of the connectors and things like that. And then other stuff we're looking at, SFP, as the fiber channel guys here will say, is they're bugging us to get a 200 gig SFP started, and we're working hard to get that project going. Okay. And this is kind of our call to ask people to join us. So we're trying to solve all these problems around higher speed Ethernet PCIe to solve these AI issues. We have participants across the industry, but we always like more to participate. And if you do, you'll be able to work on some of these high speed projects, and you'll hopefully bring advantages to your company in there. And the bar to open a new project is pretty low in SFF. You just need a couple of companies supporting your work. So it's an easy place to start something. And here's all the places you can go to get information. I think that's it. Mohammed, you've got to have one question, or I'm going to ask you a question. Anybody? Okay, then I got to ask Mohammed a question. Down here.
So on PCI, back to
yes.
Our discussions there. So there's a lot of momentum now on the OSFP XD PCI solutions. Do you see that being within SNIA at all, or how is that going to progress?
Yes, that was my question to you. But no, actually, as we're doing this, and you've sort of stepped a little bit back from that PCIe optical working, and we have started to see a little more, openness to doing more of the optical PCIe stuff. But the issues we keep coming back to is the sidebands. So, and that's something we could work on here, like you mentioned OSFP. OSFP has a limited number of pins.
Right.
How do we get those sidebands, and which sidebands do we need for AI applications?
There are some proposals, but that were put out there for QSFP-DD and OSFP-XD.
Right.
But the key thing is to, if the SIG continues to commit to having non-SRIS and full implementation of the non-SRIS common clock solution, that's not going to go very far, right? But the SRIS, SRNS implementations could be simplified and creating a common solution that would work with other protocols as well with the same hardware. So the vision is, the reason SRNS, SRIS was exciting for PCI is graduates it from a bus to an interface. But are we willing to go there? That's the question. What are you seeing in the industry in terms of willingness to go there? OCP was willing to go there, but I'm not sure if the rest of the industry was.
Well, that's what I would like, one of the things I would want to work at in the SFF group is if we define some of those connectors and those module stuff, right? So we need some more guidance, not from the PCIe group. We need it from the AI storage people that are in this, at this conference as to what those sidebands have to be. I talked to John, he said PESTI is required. How many sidebands are there? 8? There's a lot of different sidebands that are in the PCIe spec. And if they all go across one interface, that's great, but maybe we can't fit them across there. We've got separate pins for stuff. We need to define what that is. And that could be done in SFF because we're looking at AI, and maybe, I hate to say, but maybe it's not exactly PCIe that goes across there, right? But it's very similar. And some people have talked about, it looks like PCIe, but it's running at 400 gig. I mean, is that something that this group would like to see? It would seem like it, based on the presentations I've seen. John, thank you for using the microphone.
It was the least I could do. So I think there's a couple of things to differentiate. One is, what's the relationship to the interface that your module sees, which we do want to be pretty PCIe compliant. What you do behind that wall is an interesting question, and that's where opportunity awaits. One of the interesting things, as an example, PCI SIG now defines in Chapter 12 the PESTI interface, which is used in the copper link cables. That is basically a 250K UART. So that's what you're going to get as a present. The good news is, or the bad news, depending on how you look at it, given that, as you've shared, optical is a one-way cable, is you're going to have some intelligence which turns that outgoing packet, which isn't very big, into some optical signals to get over to the other side.
Yep.
You then have a 200 microsecond turnaround time to go send the other packet back.
Well, when you have Ethernet, you can manage the world at a system level using Ethernet and dump all those.
We're talking about how, and that is another potential option. This is what's currently built and architected in.
Yeah, and one thing I would say, I was thinking about when you mentioned PESTI, and we talked about some of the other sidebands, is we queried, this is public knowledge, at Google and Facebook, and they came up with their whole list. And there was a third one. I'm not sure if it was Microsoft. There was a third person, and Mohammed was there. They came up with a list. All three were different.
Yeah.
So even the end users can't decide which one of those they want. We have a connector that can't support all of them anyways. So it's been very confusing, and I think we may see a bifurcation of these where we may end up with 3 different interfaces.
There is also a push going on in some PCIe stuff right now to use USB for sidebands.
Yes.
But one of the interesting things, which is simple and relatively easy to implement, is that 250K UART. You can manage.
Well,
doing
as I
that
mentioned, a
with
UART is
functionality.
bidirectional on a single wire.
Yeah.
Fiber optics doesn't do that.
No, but you
So-
can actually incorporate the logic to basically send it one way, on the other end, have the logic available to say, oh, it's not my time now to pack it
Yep,
back.
I think that can be done.
Yeah.
Yep.
Hey, Tom. I think I'm going to try to stir the pot a little bit on SFP. What would it take for us to start a project on SFP to get 224 and
Oh. Roger? Oh, the question was, what does it take for us to start an SFP 224 project? I think we need somebody of your clout.
I would go to the guys in 11.2 to start there.
I mean, I got to be careful. I'm on both sides of this, right? So from the T11.2, we are the physical layer of fiber channel. We have said, we need this, we need this, we need this. But as you're well aware, at the SFF, projects can't start without editors. And so far, I don't want to say, because there's one company that happens to own all of this, at least from the fiber channel side of it. They're very vertically integrated. They have their own modules, they have their own chips, they have their own everything. And some of the other companies are saying, hey, that business is no longer, we don't do that anymore. And so I think we're having trouble. He's not there. He has left the chair. So we're still looking. If anybody here would like to be an editor for an SFP document, we are dying to have you participate.
Certainly, I can volunteer to ask one more question, not the document as yet. You mentioned that Microsoft favored 200 gig as opposed to 400 gig.
Yes.
Could you elaborate more on that, like pros and cons?
Yeah. So there's been two presentations from Microsoft. One was from Pradeep, I mentioned. He was the founder of Juniper, so I actually worked with him way back when. Really smart guy. He's one of the guys who's like kind of pioneered routing back in the day. And so he's a pretty, at least I respect the guy. And he is just saying that if you go wider, right, you can go more places, you can manage it better, you can get longer distances, which is, as I mentioned, the number one thing we heard from, I would say at least 3 end users. And again, this is all public, that Microsoft, Meta, and Google all came down very hard saying, look, all I want is longer copper cables, because all this optic stuff that everybody's talking about is so unreliable. I don't even see me adopting it, because I think they had statistics on failure rates of these training algorithms. And apparently they have a failure once every 4 hours, I think is what they agreed on. And they said once every 4 hours, their system goes down. And that's all this stuff about storing states and all the rest of the stuff to bring it back up. But that's a huge problem, right? And he said that's with copper. They say with optics, it's completely untenable. It just will not work. At the same time, you're hearing NVIDIA's going CPO. So it's a different message we're getting from different people. So I don't really know, but the Microsoft pitch was that, hey, 200 gig, I think he would have liked to said 100. And afterwards I talked to him about, somebody mentioned, different Microsoft presentation. Somebody from Microsoft actually said that what I'd really like is 100 gig NRZ, because that solves a lot of his bit error rate issues. The forward error correction things are much easier. He said, what I really want is 100 gig NRZ. That's my sweet spot. But when I talked to him on the side and I said, yeah, I totally agree with you. From a signal integrity standpoint, all the other issues, that's a perfect thing. I said, but I just don't see you doing it. He goes, you're right. There's just no DSP infrastructure. There's nobody really behind that. But that's really what they're saying they want, because it's more reliable, right? You get better bit error rates through the system, and all the advantages you get of wider and faster. And they claim that higher density connectors are reality today. And I've seen some of these things that say you can get twice the density of, say, I don't name any names, but what's currently used in AI applications by some of the major guys. Those connectors, they believe that they can double the density of those at the same data rate. So there you're like, okay, I can get double density, keep my data rates low, everything works together. So there's something, I think, behind that. But this just came out in the last 2 months. So it's kind of a new thing. thank you all. I appreciate the participation.